Hey guys, this is Dr. Duncan, and we're in the process of looking at the problems that are assigned with Competition Class 2. We've already done the first problem, which is pretty straightforward. This is that second problem. So let's take a look and let's get started. So here's the problem. You've probably read it on your own since you've been working on these problems yourself first. If not, you should be working on those problems first and then come to these solution videos to get a better handle on how to solve the problems if you're stumped, or to check your answers if you've actually finished those problems. So this would be a good place to pause and then reread the question so you're more familiar with the question before we go on any further. So go ahead and do that now if you need to. Okay, so looking at the question, you see that we've got two species of fish. They're living in the same environment. You're given some information about each species. And you see that the challenge over here is to draw the isoclines for each species and figure out what the equilibrium point is for both species, as well as completing the proper labeling and so forth of the Zinji, and to estimate the carrying capacity for each species in this situation. All right, so let's get started with doing that. Let's first ask the question, what is it that we need to know? What do we know now, and what do we need to know? So to get started with that, let's make a list of what we need. First of all, you need to figure out what the carrying capacity of species 1 is. Clearly, we need that to map the Zinji for species 1, as well as we need the alpha of alpha 1, 2, which is the competitive impact of species 2 on species 1. And as you might anticipate, we also need K2, which is the carrying capacity for species 2, and also alpha 2, 1, the competitive impact of species 1 on species 2. So this is just making a list of the things that we need. It's like it helps us to stay organized and focused and figure out like what the next steps are. So now let's go to the question and figure out like what do we know about these four things based on the question. So if you take a quick read of the question, you'll see that there's some wording up here that gives us a big hint. It says that when the sticklebacks have the pond all to themselves, they can reach a population size of 100 individuals. Okay, so that means that when the mosquito fish are not around, the sticklebacks are able to populate the whole ecosystem up to their carrying capacity. And so their carrying capacity is 100 individuals. So that means that our K1 is 100. All right, so if K1 is 100, how do we figure out what K2 is? Well, K2 is going to be also embedded in the question up here. So we see that when the mosquito fish occupy the same pond by themselves, so no competition around, that they grow to a population size of 60 fish. So that's our K2. Okay, so that's some essential information to get us started. And then there's more information provided that helps us with our alphas. And this is where the problem gets a bit more complex. All right, so the first thing we're going to do is to figure out what the alpha 1, 2 is. So the competitive impact of species 2 on species 1. So let's get organized a little bit more here. Let's designate species 1 as the sticklebacks, and we'll designate species 2 as the mosquito fish. And what do we know about species 1? We know that its carrying capacity is 100. Now, as you probably figured out, the clue as to what's going on with the alphas is right up here in this line, which is to say that when the two fish are occupying the same pond together at the same time, you can have 70 stickleback and 40 mosquito fish. That means that a total of 111 fish, but they're split with 70 sticklebacks and 40 mosquito fish. They're sharing resources. That means that the mosquito fish cannot reach their carrying capacity because the sticklebacks are there, and the sticklebacks can't reach their carrying capacity because the mosquito fish are there. Now, the hardest part of this word problem is to figure out what the alpha is. So we need to figure out what the competitive impact is of species 2, the mosquito fish, on species 1, the sticklebacks. So we're given this clue about the 70 sticklebacks and 40 mosquito fish living together, and that's how we're going to figure this out. So here's what we got. We know that the carrying capacity for species 1 is 100. So that's 100 sticklebacks when there's no mosquito fish around. But when the mosquito fish are around, we only get 70 stickleback. Okay? So that means that 30 sticklebacks are absent when the two species are living together. And that's an important piece of information because that tells us that the mosquito fish, these 40 mosquito fish up here, they are using up the resources of 30 stickleback. Everybody get that? So these 30 sticklebacks that are not present when the two species are living together, they are, it's these 40 mosquito fish that are using the resources of the 30 sticklebacks. Thus, continuing on with that logic, the impact of 30 sticklebacks is the equivalent of 40 mosquito fish. So now we're getting closer to figuring out what the competitive impact is of the mosquito fish on the sticklebacks. So as you might have anticipated, the way we're going to figure this out is that is by the ratio of resources used by one fish to the other. So 30 sticklebacks divided by 40 mosquito fish gives us the impact of the mosquito fish on species 1, the stickleback. Okay, and so that comes out to 0.75. So all that is to say that one mosquito fish consumes the same amount of resources as 0.75 sticklebacks. And we're able to get that because we are converting the impact of the mosquito fish onto the sticklebacks. Now, just as a sidebar here, I often, when I think through these kinds of problems, I often try to think about it like as if I'm converting currencies, say, U.S. dollars to euros or something like that. And so one way of figuring out, like, if our computation here is correct is to reverse engineer this and see if we come up with the right answer. So to check our logic, if we were to convert 40 mosquito fish to sticklebacks using our conversion factor of 0.75, then we should be able to, the math should work out to show us that 40 mosquito fish is indeed 30 sticklebacks. And of course, when you do the math, as you see here, 40 mosquito fish times 0.75, of course, becomes 30 sticklebacks. So that's just reverse engineering our math to check our math and also make sure that our logic's good and sound. And it's pretty convincing. We have figured out what alpha 1, 2 is. It's 0.75. So now that we know what alpha 1, 2 is, we can figure out how to map that Zinji for species 1, and that's good because we have to figure out what K1 divided by alpha 1, 2 is. And so if we do that, and the math's pretty straightforward here, we take the 100, the K1, which is 100, and we divide that by alpha 1, 2, which is 0.75, and that equals 133. Okay? So this value here, this alpha K1 divided by alpha 1, 2, of course, is the other number that we need in order to map the Zinji for species 1. So we've got the two ends of that Zinji line. We've got the K1 over up here at the top, and we've got the K1 divided by alpha 1, 2. So we would be ready to graph this Zinji when we're ready to graph. Okay. Now we need to figure out do the same thing for the mosquito fish. So, what do we know about this mosquito fish? Well, we're calling them species 2 for starters. The carrying capacity for the mosquito fish is 60. And following the same logic as before, if we had, when the two species are together, you only get 40 mosquito fish, then that means that 20 mosquito fish are missing when the two species are living together. 20 that's down from the carrying capacity of 60. Okay? So another way of thinking about this is that the 20 mosquito fish, the 70 sticklebacks are using the resources to equal those 20 mosquito fish that are not present when the two species are living together. So following that, we can now calculate the alpha 2-1, which is the competitive impact of species 1 on species 2. And we simply divide the total number of mosquito fish, which is 20, divided by the 70 sticklebacks, and we get 0.286. Okay, I'm going to run through the logic of that just one more time to make sure that I was clear on that, because I think it could have been a little bit more clear. So we need to figure out what the competitive impact of the sticklebacks are on the mosquito fish now, right? So that's the alpha 2-1. And we know that when the mosquito fish are living by themselves, there can be 60 of them, and that's the carrying capacity. But when they're living with the sticklebacks, there's only going to be 40 mosquito fish. And the difference between there is 20. That means that 20 mosquito fish, the resources to support them are instead supporting 70 stickleback, okay? And that's why we get this ratio down here, that 20 mosquito fish are equal to, or is basically the equivalent of 70 sticklebacks and vice versa. So this helps us figure out the competitive impact of species 1, the stickleback, on species 2, the mosquito fish. And so 20 divided by 70 is 0.286. Okay, I cleaned up our workspace a little bit here so that we can now compute and check our logic, which is that converting 70 sticklebacks back to mosquito fish actually worked out nicely. So when we multiply 70 stickleback by our ratio of 0.286, our alpha 2-1, we get 20.02, which is darn close to the 20 mosquito fish that those 70 sticklebacks that we predicted were the resources that they were using up. So these numbers match up, so it's just a way of checking our math, and we are good to go forward. And of course, our next step is to calculate what K2 divided by alpha 2-1 is, and that's going to be 60, our carrying capacity here, divided by alpha. So this is our carrying capacity up here, K2, divided by alpha 2-1, which is here, and written out for you down here. We got 60 divided by 0.286. That comes out to 209.7, or if you want, you could round that up to 210. Now we have both of the, we have all the data we need to graph the Zinji for the mosquito fish. We got the carrying capacity of K2, and we've got the K2 divided by alpha 2-1. So we are ready to do some plotting. Okay, so I've cleaned up our workspace here, and I've copied over the information that we figured out up to this point, the information that we need to graph these Zinjis. So if we take a look at our numbers, we can see that all of our numbers range between 60 at the lowest and about 210 at the highest. So we can work with that on our axes. So let's get started. First, we'll label our axes. Always want to label your axes first so that you don't get confused, and whoever's looking at your product, your work, doesn't get confused either. So we'll put species 1, as always, on the x-axis, and we'll put species 2 up here on the y-axis. And then we'll throw some numbers on here that'll allow us to graph everything we need on the x-axis. So I got 50, 100, 150, 200, and the same for the y-axis. Okay, very good. So now we can plot our Zinjis. Let's get started with species 1. We know its carrying capacity is 100. So that's this point down here on our x-axis. And the other thing that we need to graph is, of course, the K1 divided by alpha 1, 2, and that's going to be 133, and that goes on the y-axis. And that's going to come out to be right about here. And so we just need to connect those points with our line, and that's our Zinji for species 1. Yay! So we're halfway there to having both Zinjis plotted. We're going to do the same thing for species 2. Here's the carrying capacity for species 2, it's 60, and then K2 divided by alpha 21 is 209. I left just enough space on the margins of the x-axis to fit that in there. And then now we just connect the dots there, and here is our Zinji for species number 2, the mosquito fish. Now this is a good point in time to check to make sure that we've done things right. And by that I want to point out the what it says up here in the word problem, which is that when the two fish are occupying the same pond, there are only 70 stickleback and 40 mosquito fish. So reading between the lines here, we know that this is a situation where both species can coexist. And so if that's the case, then where these curves cross, right about here, should be approximately 70 stickleback and 40 mosquito fish. So let's see if that's the case. So reading down on the x-axis for the sticklebacks, I'd say that's about 70, right about there, more or less. And if we read over here on the y-axis, that's roughly about 40 for the mosquito fish. So things are looking good. I think we've got a good graph here that represents the problem pretty well. But we're not going to stop here. We're going to continue because we want to make sure that we haven't messed up, we haven't had any problems with our logic and that sort of thing. So let's look at graph space here and see if graph space also predicts that we get an equilibrium at 70 stickleback and 40 mosquito fish. Okay, so for starters, let's look at this lower left part of the graph space. In this situation, we're looking at where we're in this zone where we're in the zone of positive growth for the sticklebacks. That's represented by the black arrow here. See, we're below or behind the black line. We're in the zone of positive growth. That is to say that there's enough resources here for the stickleback population to continue growing. And of course, the direction for stickleback growth is to the right when the population is growing. So we get that arrow to the right. Okay. And then for species number 2, the mosquito fish, we are also in positive growth territory. Here the arrow is up, corresponding to the y-axis. You know, where you've got the higher you are on the y-axis, the more mosquito fish there are. So we're getting growth in the mosquito fish, as indicated by the blue arrow here. And then our vector sum diagram is, of course, this red dotted arrow that shows the direction of the two populations when plotted together, because any point out in this graph space represents both populations, and so we're interested in the direction that they would grow. And because they're both in positive growth territory, the directionality is up and to the right. So that's how we do our vectors and figure out the direction of the populations when graphing them together. Okay, so now let's look at the next quadrant. I like to look at the upper right quadrant of our Zinji space here. And up here, of course, we're looking at we're in negative growth territory for both species. For species number 1, we're in negative territory, so the arrow is to the left. That's the black arrow. And then for species number 2, we're in negative growth territory, so that's a down arrow. For species number 2, again down relative to the y-axis because species 2 is on the y-axis. And then the growth, the combined Zinjis, I'm sorry, not the combined Zinjis, but the combined vectors have us looking at the ratio of the two species being plotted. Being plotted together is down and to the left. So that's headed towards, of course, where we know the equilibrium should wind up, which is right about there. So far so good. Things are checking out. Things are making sense. All right, next, let's look at the lower right-hand quadrant of our Zinji graph. And down here, we see that we're going to have we're in positive growth territory for species 2, so the blue arrow is up. And then we're in negative territory for species 1, so the black arrow is pointing to the left for lowering numbers of sticklebacks because we're beyond the stickleback Zinji. And the net directionality of those two when plotted is going to be up and to the left, which again is leading towards our center of our plot. And then, of course, when we plot the final quadrant. It's like a mirror image of the previous one, the third one that we did, and we see that the ratios of the two species is moving down to the right, again towards the equilibrium point at the center here. So everything's checking out, it's looking good, and we've got a graph here that shows us that we've got coexistence of the two species with 70 stickleback and 40 mosquito fish, just as we were asked to do with this problem. Now this particular problem has two parts. We've just solved part A, if you will. In part B, let's go to another sheet here, clean things up a little bit and get started with part B. So in part B, we see that a virus has attacked the mosquito fish, shifting its isocline down so that its abundance when alone is 40 individuals, and alpha 2,1 becomes 0.667. So this is nice because they tell us both what the carrying capacity is and also what the alpha 2,1 is. So that makes our job a little bit easier for this next problem. So our first step, of course, is to just carry over the information from before that isn't changed. And of course, that's the carrying capacity for species 1, the sticklebacks, and that's still unchanged at 100. And K1 divided by alpha 1,2 is still 133. So our Zingi for species 1 stays the same. For species 2, our new carrying capacity is 40, as stated in the question. That's easy. And our alpha is 0.667. So that means that our next step is to divide the alpha into the carrying capacity. So 40 divided by 0.667 is 60. Okay, so just one more time to make sure that that's cleared. We're dividing the carrying capacity, which is 40, divided by the alpha 2,1, which is 0.667, and that comes out to be 60. So now we have everything we need for plotting the isocline for species 2. We've got the K2 divided by alpha 2,1, and we've got, of course, K2, which is 40. So what is that going to look like? So there's our K2 for the mosquito fish at 40, and there's our Zingi plotting over it with a K2 divided by alpha 2,1 at 60 on the x-axis. So if we now plot our vectors to see what's going to happen, we see that this upper right section, or the majority of our graph space here, is negative growth territory for both species, so the combined trajectory is down and to the left. If we look at the very lower left-hand corner, we see that the combined trajectory of both populations is up and to the right because both populations are growing. Both populations are below the Zingis. Now, and finally, we need to figure out what happens in this middle zone here. And of course, this is going to tell us whether it's going to swing towards species 1, the sticklebacks, or swing towards species 2. And if you remember how these outcomes are structured, you already know what the answer is here. But if you don't, you can still use these vectors to figure it out. So, and I'll slow down here for that reason. So the black arrow here represents the population growth for species 1. We're in positive growth territory for species 1 because we are below the Zingi. So the arrow is over and to the right. I'm going to draw another arrow there just to emphasize. Positive growth for species number 1. But we are in negative growth territory for the mosquito fish, species 2. And so that's represented by the down blue arrow here, indicating against the vertical axis a decline in the population size because they are way past their isocline, their Zingi here for species number 2. So the combined vectors, growth for species 1 and decline for species 2, leads to a net direction of the ratio of the two species down and to the right, and that's what we see here. And what would happen over time is that the populations would drift, species 2 would get smaller and smaller, and species 1 would get larger and larger until it reaches its carrying capacity, and eventually species 1 wins. All right, so that's a wrap with explaining the two problems that are part of the competition class 2 exercise. If any of this is confusing, go ahead and watch the videos again, and if it's still confusing, be sure to reach out to your instructor, who's always happy to walk you through this, maybe come at it from a different angle and help you out in ways that'll connect with you. So that's it for now, so I'm going to sign off.